Yeah, so before I do that, so let me just give you a bound of channel capacity. I mean, okay, so this is just an ordinary bound for all possible channels. Okay, so this is a bound, specifically an upper bound of channel capacity. So by channel, what I mean is, okay, we have some X, we have Y, and here we have this probability of Y given X. Okay, and there is a probability distribution here, which is, let me write it as, that this is the, and this is the source alphabet. Source alphabet. So there is a probability distribution on this sample space, and there is some another, you can say the output alphabet. So it is like A1, A2, A in here, or A1, A2, AK here. Okay, whatever business number. Okay, and here I have some B1, B2, BJ. So this is S. Then, and what was the channel capacity? The channel capacity was max over Q. So Q is the probability distribution defined on this, say, calligraphic X on the source alphabet. So this is maximum of the mutual information, or the average mutual information of X and Y as random variables. Okay, so let me give you a generic bound. So basically what we know from the definition of average mutual information, this can be written as up to entropy. So entropy of Y, let's say minus H of Y given X. Obviously, we can say this is less equal to HY because other one is non-negative. And we already have, earlier we discussed that there is always a bound for this entropy, which is less equal to the log of number of elements in Y. Okay, so similarly, instead of using HY, you can also write expression using X. And similarly, we can show that I of XY is less equal to log of mod of number of elements in, so number of source letters basically. Okay, so therefore what we can say is, and of course this is a non-negative number, average mutual information, this we proved earlier when we defined it. So this, therefore we can say it is, the channel capacity is less equal to this and minimum of this log of Y. Okay, so this is a generic bound, but this may not be of any interest, but at least, okay, there is a bound for this. Now we'll be calculating some channel capacity of some channels. So let us first consider this binary symmetric channel. Binary symmetric channel. And we know what is it. So we had this 0 and 1 here. These are the source letters, and 0 and 1 here. And there is a crossover probability, which is 0 can go to 1. And let's say this crossover probability is epsilon. So this is epsilon, then it is 1 minus epsilon. And it is symmetric. So here also we'll have a similar situation. This is epsilon, and this is 1 minus epsilon. So this is my channel, and I want to find its capacity. Okay. So, and so what you have to do here is, there is a probability of 0. There is a probability defined here for the distribution. So this is the set of all probability vectors. Here I can say this is some p, and this is some, let's say 1 minus p for any value of this p lying between 0 to 1. Basically, this is my probability space, or let's say the set of probability vectors that we are talking about last day, which forms a convex set, right? So yeah, so P could be anything. So 1 minus P could be accordingly that. And then our question will be, for what value of P's, for what distribution it will give you a maximum, and what is the value of this maximum. So now I want to calculate max of this. So max of P here, I can say, and this is I X given Y, and the channel is given to me. So this transition probabilities are given to me. Okay, which is defined. So there is only one parameter, which is epsilon here. Now, if you want to do that, I can use the formula of I of xy. And as we discussed before, it could be like h of y minus h of y given x. But if you want to compute h of y, I also need to know what are the probabilities here. What is the probability of 0 here? What is the probability of 1 here? Because y is a random variable. Unless I know the probabilities, I cannot compute that. So first of all, I need to compute the probability of, so here y, where y could be equal to 0, or it could be equal to 1. And here, let's say a generic variable x could be 0 or 1. So let us first find out what is the probability of y. Okay, so we know how to calculate the probability of y. So this is sum of, you can say p x test and p of y given x test could be equal to 0 or 1. Okay, so this is the definition of probability. This is the way we calculate probability using the conditional, using this conditional probabilities, or you can say the transition probability. So if I do that, so then this is nothing but probability of x test equal to 0, or I can just anyway. So let me write it down: y and x test equal to 0 plus probability of x test equal to 1 times probability of y x test equal to 1. So these values are given to me. So this conditional probability. So let us put that. So let me now remove the symbol x test. Let me just write p0 and probability of 0 given 0 when y is 0 plus probability of 1, probability of 1 given 1. Sorry, 0. I'm calculating for 0. So 0 given 1 when y is equal to 0, and when y is equal to 1, it will be probability of 0, probability of 1 given 0 plus probability of 1, probability of 1 given 1. This is for y equal to 1. So basically then what I have here is the probabilities. So this is P, because I assume that probability of 0 is equal to P here. Okay, probability of 0 equal to P here. So if we just replace this probability of 0 by P, so this is 0 and this is 1 minus epsilon. Okay, probability of 0 given 0, so this is 1 minus epsilon and plus 1 minus P times probability 0 given 1, which is epsilon. So if y equal to 0, and this is similarly, we will have P epsilon plus 1 minus P 1 minus epsilon when y equal to 1. Okay, so I already know the probability of y, so I can compute h of y. Now I need to compute this h of y given x, so that's the conditional probability. So, but what is the formula? How do we calculate this conditional probability, conditional entropy? So this is, if you remember the formula, so it was px h y x equal to x, and then x equal to 0 to 1 and y equal to 0 to 1. So here, okay, basically if you remember the formula, so it will be over x over y. In here it was pxy. I can write it like p y given x and log of 2 1 by p y given x. So this is the formula. Anyway, so if I write this, I know all this now. P of x, I know this. Okay, so I know the formula. So let us write, what is that? So if I take all values of x and y, so this is x equal to 0 times probability of y equal to 0 given x equal to 0 log 2. Let me just skip that 2. 1 of probability of 1 by probability of y equal to 0 given x equal to 0 plus probability of x equal to 0, probability of y is equal to 1 given x equal to 0, then log of 1 by probability of y is equal to 1 given x equal to 0 plus probability of now I put x equal to 1, probability of y is equal to 0 given x equal to 1, and log of 1 by probability of y equal to 0 given x equal to 1 plus probability of x equal to 1, probability of y is equal to 1 given x equal to 1, log of 1 by probability y is equal to 1 given x is equal to 1. So let us now put all the values. So then this will be probability x equal to 0. Okay, if I just calculate this, this will be p 1 minus epsilon, okay, log of 1 by 1 minus epsilon plus u epsilon, sorry, p epsilon, yeah, log of 1 by epsilon plus 1 minus p epsilon log of 1 by epsilon plus 1 minus p 1 minus epsilon log of 1 by 1 minus epsilon. So which now I can little do a computation, some addition, some subtraction. So it will give me sin log of 1 by epsilon plus 1 minus epsilon log of 1 by 1 minus epsilon. So if you do a little bit of calculation, algebraic manipulation, it will give you like this. So this is what, this is nothing but entropy of epsilon, right? So this function, with this notation we used earlier also, this is nothing the binary entropy. B stands for the binary. So this is the binary entropy function. So therefore, what is happening here, now I can write, I have the expression of, sorry, I x y. So mutual information is hy minus h of y given x, which is equal to what? Hy will be equal to this one. Okay. I know the probabilities of this, y equal to 0 equal to 1, so I can compute the entropy of this. Similarly, and this entropy is already given to me. Okay, so what we'll have is basically p 1 minus epsilon plus 1 minus p epsilon log of 1 by, so this is, I'm writing it from here. So yeah, here. So this times log 1 by this, okay, plus this times log 1 by this. So this by p epsilon plus 1 minus p times 1 minus epsilon. Okay, so if you take the common thing, then this will be this plus p epsilon plus 1 minus p times 1 minus epsilon, and then log of 1 by p epsilon plus 1 minus p times 1 minus epsilon, and then minus h p epsilon. So this will be my function. Okay. So now I want to maximize this. Okay. I want to maximize this function. So maximum of this is equivalent to say minus times minimum of this, right? So okay, let me just write it down. So C is maximum, okay, of P. Okay, P is lying between 0 to 1, by the way, here. And then IXY. So for IXY, I know that this is the value. Okay, so this entire thing is IXY. So this is what is IXY. So the same thing can be written as minus of minimum of. So 0 less equal to P less equal to 1, and we'll take the minus of this, so which will be like this. Sum, okay, sum P times 1 minus epsilon plus 1 minus P times epsilon. I mean, you can do this manipulation. I'm just writing it down. U of, so log of, it will be P epsilon plus 1 minus P times 1 minus epsilon. Okay. And then there will be, oh, okay, I think after I did it, some calculations so that I don't have to do it and do some calculation mistake. Okay, so this will be this times something. And this something will be something like this. P epsilon plus 1 minus P times 1 minus epsilon, and then there will be log of something. So there will be log of P epsilon plus 1 minus P times 1 minus epsilon, and then there will be plus H B epsilon. So this is the function. Now I need to optimize this. So what I can do is I can take the derivative. I need to find out the derivative, and then I need to put that to be equal to 0, and then I have to find the value of P. Okay.
Sir,
So if I do that, yes.
sir, I think the first log function will be different. The first log term.
This one.
Yes.
Yeah.
Like
Okay.
that would be p into 1 minus epsilon plus 1 minus p into epsilon.
Okay. Okay. So anyway, so this is the idea. I mean, I may have done some mistake in the calculation. Okay. So yeah, this is the idea. So you'll get something, right? You'll get some function here. Okay, some function you'll get. And then you have to take the derivative of this. Okay, let's say this function is some function of P. Okay, whatever you can add, you can calculate it and you can see what is the function. Maybe I have done some mistake. So this is a function of P. Okay, now I need to take the derivative of this. I mean, you have to like minimize up then this 0 less equal to P less equal to 1 sum FP, and then okay minus of this, and then you have to take derivative of this with respect to P, and then you have to put the value that this would be equal to 0, and then this will give you some condition. And I think if I am right, the condition will be something like this: P times 1 minus I think epsilon plus 1 minus P. So this will give you this 1 minus P times epsilon. Okay, so this will be equal to 0. This will give you this equals to this. So this will be P times epsilon plus 1 minus P times 1 minus epsilon. Something like that it will give. Okay. And then for which value of P, okay, this equation is satisfied. That is what we have to find out. And then you can see that this will be satisfied. Okay, this will be true if P is equal to, let's say, P star, for which it gives you the minimum will be equal to half. And then you can again put this value on C, that this is the maximum of this when P is equal to half. And then if you compute that, this what is the C, if you put everything, okay, then C will be equal to, I mean, if you put P star equal to half, then this is like F of half, which will give you like 1 minus HP epsilon. I may have done some mistake in the calculation whenever I'm writing it down. Okay, but this is a very long calculation. This is what I wanted to tell you. This is a very long calculation. Okay, so this is how you can do go about it if you want to find the channel capacity for this simple channel. But now I'll tell you a smart way of doing it. You don't have to do, I mean, this is a straightforward calculation, but you have to use some common sense. And if you use common sense, then you don't have to do this much big calculation actually. Okay,
Sir,
so yes.
sir, can we use a uniform distribution which you directly maximum value.
Yeah. I'm telling. No, so I'm telling you that. Okay. So yeah, I'm telling you that. So you can use some common sense. What is the common sense? Now I'll tell you. You can. This is a straightforward way of doing it. The maximum. You are maximizing some function or some parameter. So the idea is this is a convex function and this and that, and then take the derivative, make it equal to 0, and then find out the value for which it is maximum. Other way of this is now use the common sense. This is the method. Now you have to use common sense. So if you do it using common sense, then what is happening here is I of x, y is equal to, you can say hy plus h of y given x. And we already have computed this y given x, which is hp. So this is basically 1 by y. This will be minus hp. H minus of hp. Okay, this is how you have, or maybe you can say hp, or what I'm writing. And this is epsilon. Okay. So this. Okay. Now, we always know that this is less equal to log of the number of the sample points in y, so which is 1, right? So log 2, 2. So because it is 2, 0, and 1, so this is log 2, 2 minus this hb epsilon, which is equal to 1 minus hb epsilon. So now here we already see that this function is less equal to this for any probability distribution for the input random variable. So for any value of p, this is always the case. Now, so here there is an inequality. If somehow I can make this equality, then I get to know that for that particular p, I mean, I'm looking for some p, if I have some value of p for which this value, the entropy will be equal to 1. Okay, for that value of p, because see, here I have x, here I have y. Now, if I want to calculate this is 0 or 1. If I want to calculate the probability of 0, probability of 1 here, I need to use the probability here, probability of 0 here and probability of 1 here. Okay. So now the question is, see if somehow I can show that this inequality is actually an equality, then I can be sure that okay, this is achieved. So this will always be the maximum, because for any p, this is less equal to this one. So now, and this is a constant. So now the idea will be, can I have some value of p for which the entropy of y is exactly equal to 1. So entropy of y is exactly equal to log of 2 and 2. And this we have seen earlier when we computed, we have computed the entropy of random variables. Then you can see that if I take this to be equal to half and this to be equal to half, then you can check that this will always be equal to 1. Okay, you can check that using this formula, whatever I used here, this hy and this thing. Okay, p of y. So if you take p equal to half here, so then you will have y equal to 0 equal to half, and here, okay, if you take p equal to half, this is 1 minus epsilon, and this is plus half 1 minus epsilon. So this will be equal to what is that? 1, and here y equal to 1. Also, you have the same thing. It is p equal to half, so half epsilon, and yeah, so you have to compute this. So half of 1 minus epsilon. So epsilon can cancel, and then this is equal to also half. So then half log half plus half, I mean minus half log half minus half log half. So that will give you 1. So so this can be made equality. This can be achieved when you take value of p to be equal to half. So if you take this to be equal to half, then this can be achieved. So this inequality can be made equality, and hence this should be the entropy. So that these many bits, not the entropy, but the channel capacity. This will be channel capacity because I of xy is less equal to this, and here there is an inequality sign which can be made equality for some value of this p, and hence this should be the entropy of the channel. So sometimes what happens is you don't have to solve an optimization problem. You can use your common sense and you can find out what is the channel capacity. Okay, now I'll give you one more example where this logic will fail. I mean, this logic need not be I mean, you cannot apply this logic for all possible problems. Okay. So now let me give you one more example of a channel. We want to compute the channel capacity for that channel. Okay. So my second example is something called binary eraser channel. Okay. Binary eraser channel. But if you practice this, I mean, this calculation I am showing you, this is a long calculation because I am doing all possible calculations. But if you are smart enough, okay, you can do this. For example, you can calculate this POI in just one line if you practice it. Okay, you can do it just by looking at the channel. You can, and all the probabilities, you can directly compute this. Okay, so for that you need practice. Okay. Similarly here, you can directly put from this line to the last line. You can directly do that if you practice this. Okay. Okay. So
Sir,
let me. Yes.
sir, how can we write that h of y is less equals to log 2 base 2? That
Then you have to go and see my lecture note where we discussed about entropy. Okay. Here we use that. In fact, today also used it. Here you see, here I used it. So hy less equal to log of mod of y, which is the number of alphabets for y. We proved this thing actually in where we talked about, when we talked about this entropy, that entropy is always less equal to log of the number of sample points. So you can see my lecture notes, and or you can type it in Google that this is always the case. Okay, so binary eraser channel. So this is also a nice channel, and this is also a very simple channel. Binary here, it means this there are only two inputs, 0 and 1. But there can be an eraser. So sometimes the bits can be erased from during the transmission. So it is called 0, 1, and there is one more. This is E. E stands for error. Okay, that means somebody sent 0, but it is erased. So there is nothing. Okay, so this symbol, let me write it as E, or you can write a blank symbol. Okay, the same thing. So let's say this is equal to 1 minus some epsilon, and this will erase with some probability epsilon. And here also same thing, 1 minus epsilon, and there is a chance that it can get erased with probability. If I write epsilon, there is confusion between it. Okay, no problem. 1 minus epsilon. Okay, what I'm writing. This is epsilon only. Okay, yeah. So let us consider this channel, and this is what is called binary eraser channel. Okay. Now see, if I want to compute its channel capacity, what is that? So it is C, which is equal to max over some Q or whatever, the PX, let's say. Yeah, the X, here is Y. Okay. So this is I, okay, X, Y. So this will be equal to max of PX and HY minus H of Y given X. So again, here you can compute this H y given x using the previous formula, and you will see that this will be nothing but h of epsilon. So you can do that computation. So let me write it as here, px hy minus h epsilon. Okay, you can compute that using the same formula like I used here. Okay, here. So it's the same similar thing will come here. Okay, so once you do that, now this is this case. Now, so basically what I have to do here, I have to find this value of P, or instead of Px, I can just write P, because probability of 0 is P and probability of 1 will be 1 minus P. So I can simply just write P. So then I have to maximize this, and this is constant. This only depends on epsilon, which is given to me. So basically I have to maximize this. Okay. So I have to maximize the entropy of Y for some value of P, which is here. Okay, for some value of P, or at least is 1 minus P, something like that. Okay, so for which value of P this HI will be maximized? That is the question now. Okay, Now say if I want to use other trick, the trick we used in the previous channel, so then this will be less equal to log 3, okay? Log 3 and then minus h epsilon, okay? So yeah, log 3. But the question is, can log 3 be a value of HUI for any value of P? I mean, does there exist any value of P and 1 minus P such that HUI will be equal to log of 3? And the answer will be no. So this is homework. Just try to find out why it is not, okay? You can just check it. This is homework, that there is no P for which h of y will be equal to log of 3. So this trick will not apply here. Okay, so this will not be possible. There is no such P for which this will happen. So you cannot make this inequality to be a equality. Okay.
Excuse me, sir.
So then,
Sir,
yes.
can we find it other way? Means entropy of x minus x given y. I think it would be
Yes,
easier
yes.
because in that case it will be 1 because because there is only two inputs, 0 and 1.
You can try that. Okay, you can try that.
Yes, sir.
Okay, you can try that. Okay, so now, so since I have no way out, so what I'll do, let us now, so basically what I have to do, I have to maximize this h of y. But for h of y, how do I calculate h of y? If I know, let's say the probability of 0, let's say it is some p1, it is some for pe, it is some p2, and it is some p3. And this can be computed using the above formula, which I already discussed. In terms of, so p1 will be a function of p, okay? Or let me write a different notation. All everything is p here. Let me write this to be equal to pi, and this to be equal to 1 minus pi. Okay. So p1 is in terms of pi. P2 also will be in terms of pi. What happened? Just can you guys see now? This, can you see the screen?
Yes.
The note. Okay. Okay. So yeah, what I was saying. Yeah. So this P1, P2, P3 you can compute, and in terms of P. Can anybody tell me what will be P1? Directly from the channel, looking at the channel. If probability of 1 is pi and probability of 0 is 1 minus pi, what will be P1?
So 1 minus pi into 1 minus epsilon.
Okay. So entropy of this will be then basically entropy of this 1 minus pi times 1 minus, what is that? Epsilon. This is for P1. And what is P2? What is P2?
So P2 depend on 0 and 1.
Epsilon.
That will epsilon alpha.
Okay. So it is epsilon. And what is P3? What is P3?
It will be direct pi into 1 minus epsilon.
Okay. So this is pi into, so you can just looking at the channel, you can compute. Okay. So you need a little bit of practice, like how it is defined. 1 minus epsilon. Now, so what is the formula here? Entropy of these 3 points. Okay. I mean, this is the probability vector here. Okay. So this will be what? Minus 1 minus pi times 1 minus epsilon times log of this 1 minus pi 1 minus epsilon, then minus epsilon log of epsilon, then minus pi 1 minus epsilon times log of pi 1 minus epsilon, right? So this is my hy. So now if you do a little bit of calculation, so what I can do here? Okay, so there is a multiplication term here. There is a multiplication term here. You can write in terms of like you can split it. Okay, so this multiplication into addition, and you can do everything. So I'm not good at calculation. Let me do it. This into 1 minus epsilon. So this will be okay. So if I take this common, this will be log of minus epsilon pi plus. Okay, just look at my calculation and let me know if I'm doing something wrong. And this is minus epsilon log of epsilon minus pi 1 minus epsilon. Okay, then log of pi plus log of 1 minus epsilon. Now what I can do? Okay, I can combine these two using this 1 minus epsilon. So if I do that, 1 minus epsilon, let me take this as common. Then there will be a term here, minus of 1 minus pi, right? Yeah, and then log of 1 minus pi, right? And there is another. Okay, here also I took common, right? So 1 minus epsilon. How do I write it? So okay, I should not write it here. Let me write it here. Log this and then minus pi log of pi. Okay, this is first part, and the remaining part is let me say the remaining part as it's epsilon log epsilon, and then here this part will remain, this part will remain. Okay, so these are same, right? There is pi, there will be 1, so it will be most likely minus 1 minus epsilon log of 1 minus epsilon. I may be wrong, but anyway, so it is something like that. Okay, let me check whether it is coming to, because I know the answer. So 1 minus epsilon, and here there is, yeah, so here actually it is the h of pi. Okay, and okay, I think I'm correct. Plus here it is h of epsilon. Okay, so yeah, so now what we have is basically, so what is my channel capacity? Oh, I was writing. Okay, just a minute. So therefore, what we have is C is equal to max of some, what was that, pi, right? What I have, pi. So this is our pi, and then I had hy, right? And then, okay, that was epsilon, right? Yeah. So h epsilon. Okay, so this is nothing but then max over pi, and then h I already got, so it is 1 minus epsilon h pi, h of pi plus h of epsilon minus h of epsilon. So this will get cancelled. So this is basically max of pi 1 minus epsilon h times pi. So which is what? This will be maximum. What will this one? The maximum value of this? What is the maximum value? What is the maximum value of this h epsilon? You remember we had drawn this picture, right? Or the this. So this is half.
Pi equal to half.
Yeah, half. So pi equal to half, it will be maximum. So it will be, and the value of this will be equal to 1. So it is 1 minus epsilon. So for pi equal to half. So for pi equal to half, that is for the uniform distribution here in the input random variable. So that will give me the maximum, and this maximum value is 1 minus epsilon. So now here we can see that. So I did not use that trick because it cannot be applied here using this less equal to. But here also I did not use any derivative. So derivative is always a way out. But sometimes we need not use the derivative, and still we can compute the channel capacity. This is the message, okay, with these equations. And you can use, I can calculate channel capacity of different functions, and you can see like what is going on, okay, how to compute this, how to compute the channel capacity of different kinds of channel, okay. And I gave 2 problems also in the assignment, okay. This is very important thing, but the message is you always, I mean, you don't have to use the concept of derivative and this and that to compute the maximum value, okay. Okay, so this is where we end for this channel capacity and other things. Now, what we did last day or yesterday, we talked about converse, okay, converse of so the channel coding theorem, okay, and we said okay, so the converse of channel coding theorem. So we actually did not prove the channel coding theorem. We proved the converse of the channel coding theorem. Okay, and we said okay, the final conclusion was okay. Let me not write the exact statement, but the final conclusion was like this: entropy, the source entropy. If it is a source entropy per unit time, it is bigger than equal to that. I think some Ts by Tc. Okay, so what was that? N times N by L, right? So L times C. No, I think this is the reverse. Tc by Ts. Okay, how I am this? I think it was N by L, right? So anyway, so it is something. Okay, let me fix this later on. Okay, whether it is correct or not. So this is in time C. Okay, if this is the case, then so per unit time, then the probability of error is positive. So this is what we have done. Probability of error is positive. So that means if you, I mean, you have to recall this diagram, okay, the block diagram of the communication system, and then you see that if I use this protocol for my transmission through the channel, transmission of bits, let's say, then there is always a probability of error. And what is the channel coding theorem? Channel coding theorem says you can make the probability arbitrarily close to 0, okay, when this is not happening. So for this, it is always bigger than this, then it is always an error. So we have to send, so we have to have the source entropy should be less than, okay, should be less than equal to the channel capacity, or this times channel capacity. This is what we had, right? Yeah. But so the question is, how do we prove that? How to do that? But see here, I mean, if you recall this diagram, see here that this statement of channel coding theorem that if it is less equal to C, then there is the probability of error will be close to 0. That is independent of your coding scheme. It has nothing to do with coding scheme. So by that statement, that bigger equal to this condition. I mean, this condition, if you replace bigger than by less equal to, let's say, that means what he's trying to tell you is you can design an encoder. So I mean, okay, let me go to the picture here. What is that picture? So if you just look at the picture of this communication channel, yeah, here. So if you look at the picture of channel, so he does not say anything about this part. So how you are encoding this, okay? And how you are decoding this is independent. So basically, the message here is of this theorem that you can possibly design an encoder. So this process you can do of your own, okay, such that it will guarantee when you are sending that this channel through this channel, when you're sending that, it will guarantee that source entropy is less than or bigger than the channel, no, not bigger than, but the less than the channel capacity. Then we can achieve what he's saying, that the probability error will go to 0. Okay, so then the question will be, how do I design, okay, my encoder? How do I, so suppose I want to send this, and then how do I design my n and l and x1 and x2 and xn and v1 v2 I mean, how do I make this kind of a map from here to here such that, okay, that can be achieved? So the source entropy is less than the channel capacity, less than that can be achieved, something like that. So because it is independent of what is happening here. Okay, this process of encoding, okay, is independent of what is happening here. In fact, if you closely look that this, so suppose you generate U1, U2, UL, so the input here is, let's say, set of binary digits. Okay, okay, let me write it here again. Let me draw this diagram. Otherwise, that is very messy diagram. So what we are trying to say here is, okay, you have this source, and here you have source encoder, and here you are sending some binary digits to this channel encoder. Okay, and then you are using a channel which is noisy, and then you are decoding it. So there is a channel decoder, and there is a sequence of binary digits, and there is a source decoder, and there is your destination. So what I'm trying to tell you here is that if you look at this part, that you are sending some binary digits, and then this is passing through this channel. So this part, I mean, whatever way do you do it, like from this U1, U2, UL, you are generating this x1, x2, xn. Okay, how do you do it? That is independent of the conclusion, because the conclusion is about passing through this. Okay, the source entropy should be less than the channel capacity. Okay, so the question is, how do I convert this? So, okay, so if you generate a code word for U1, some binary number, let me just take a simple example. Let's say it is 001 for U1. And then for U2, it is something 100. Then for U3, it is something. So this way you will get a very big length, let's say, binary digit, okay, a sequence of 0 ones. Now we are passing through this. Now the question will be, how do I design x1, x2, xn corresponding to this? This part is independent of the conclusion of the theorem. So then our motivation is, can I develop a mechanism of this part from U1, U2, UL to x1, x2, xn such that, okay, I can achieve that source entropy is less than the channel capacity. Can I achieve that? Okay, that's the goal here now. So now if I want to do that, now see here, even this is sequence of binary digits, I can choose a different scheme for x1, x2, xn as well. Nobody stops me. Meaning I can say, even it is 001 or something like this, or maybe I can make it a block, okay, of some numbers, and then I can design some numbers here, okay, but the alphabet here is different from alphabet here. Maybe I can have alphabet 0, 1, 2. That could be a process. Okay, because this is in my hand. How do I want to send it? So the question will be, how do I develop this mechanism? How do I do this coding again here, such that from binary digits to some more digits? It could be binary, ternary, whatever. Okay, how do I do this such that I can achieve that source entropy is less than the channel capacity? Because if source entropy is bigger than channel capacity, then I'll have a problem. The probability error is always positive. So I don't want to do that. I want source entropy to be less than this. So question is, can I do this? How can I do this such that probability will guarantee? So I will play with my coding encoder now. Can I develop some encoder for which probably I can develop a scheme which will do that even if there will be an error that can be rectified or something like that. Okay, I'm looking for that option now. So yeah, so this is actually called the topic of block encoding. Okay, so this is called block encoding. So I want to encode this in terms of block. Now I'll tell you what we are trying to do here. Okay. Okay, so now here you have to focus, okay, a little bit. Now what we said last day or yesterday, that there is a TS and there is a TC. Okay. TS is what? TS is the time interval, the time gap between two source letters. And TC is the time gap between two input, channel input letters. Okay. Okay. Now let me focus this problem locally. Okay. So what we're trying to say? Locally means what? Let us say I have U1, U2, UL, doesn't matter, whatever it is. But let us set a time TS which corresponding to, let's say I can say TS seconds for the one binary digit. Okay, so let me define it. So I'm changing my definition of TS and TC now because I have to focus it on locally. Okay, that how much time it will take to send or to convert. So okay, let me write it down. So here, okay, suppose, okay, suppose that binary digits or bits, okay, get into the channel encoder at a rate 1 bit, okay, in TS second. Okay, and let me define my TC. So suppose the channel, or maybe the channel encoder, okay, transmit one channel digit. So I'm not writing here binary digit bit. I'm writing here channel digit because I'll give you example. Okay, so channel digit means I can change my coding scheme here. I need not consider it as binary code. I may convert the 0 ones into some 0 1 2 0 1 2 3, doesn't matter. Okay, I can change this also, not a problem. So that's why I'm writing channel digit. Okay, suppose that the channel encoder transmits one channel digit, okay, in, let's say, TC seconds. Okay. Now what is happening here? Suppose I have now this L, okay, I'm replacing now by another notation L. So what I'm trying to tell you is, suppose I am here given L number of digits. So this is L, you can say also binary digits. Okay. Now this will reach to some n. Okay, let's say some n channel digits. Okay, now I want to have, so for each binary digit, get into, this is my channel encoder. Okay, this is my channel encoder, which will convert this into this one, and then it will transmit to the channel. So this L binary digit, for each digit, okay, get into this, and the time is TS seconds. So for L, it is L time TS seconds. TS seconds. Now when it is transmitting through this channel, it takes the time TC, and how many for one channel digit, and how many digits are there? Let's say n digits are there. Now, in order to make a good synchronization of the entire process, I am assuming that I want to have this so that to avoid any kind of time delay, because this is the total time here and this is the total time here in terms of number of digits. So if this is the thing I want, given this input as L binary digits, I should define. So in order to achieve this, in order to maintain, let's say, okay, in order to maintain, let's say, synchronizations, okay, okay, of time, okay, set, because n is free, it is in my hand. I know time, I know L, I know TC, I know the times, let's say. Now I want to fix what my n is. So I want to fix this n to be equal to this floor function L TS by TC. Now, if I am lucky, okay, so if I'm lucky, then this is, I may get, this is an integer. I'll give you an example how it is integer. Okay, don't worry about that. So I can have this as an integer. Otherwise, what I'll do, so if L TS by TC, if this is an integer, okay, then I already have the value of n. Okay, I don't need to do anything. But if it is not integer, then I have to put some ad hoc value. Maybe, so that's why I wrote it as a floor function. Some dummy digits I have to put, there's some dummy channel digits in order to make everything equal. So if you give me L number of binary digits as an input, I have to produce n number of channel digits such that at one time of use of this channel, the time it takes and this time is produced, so I can send everything all together. Okay. Now what I'm saying for that is that n I will choose like this so that there is a time synchronization, that one comes, then one goes, and then another comes, and then another goes. So there is no like of a decay channel. There is no delay. There is no channel delay. That is what I want to do. Now once it is passed through this channel, okay, once it is passed through this channel, so then this will again get into the channel decoder. What will channel decoder do? So for channel decoder, the input is n channel digit. Now then again, it will convert this into L binary digits. Okay, and then this will interpret the given message M, let's say, whatever the message is. And then we need to check whether there is an error or not. If there is no error, let us say that is a good in the coding scheme or something like that. So I need to calculate the probability of error. I need to develop this encoding scheme through this mapping L binary digits to N channel digits. Okay, so my focus will be then on this part, like how to develop a coding scheme from here, which will take input as L number of binary digits and give you an output with N number of channel digits. Okay. Now another catch here is how many such binary. So every time, now say here, this is a nice thing to observe. Every time you are, so this is my channel encoder. So every time you are giving an input of length L, capital L. But how many such inputs could be there? So that number is 2 to the power L. Okay, if this is an integer, then everything is okay, then we are done. We are done. Otherwise, we may use some. I'll talk about this also again. What do I mean by dummy digits? Otherwise, we'll use some dummy digits to make that. So this is a positive number. So that's why I use the floor function, some dummy digits. Meaning what? Suppose it is 1.5. Okay, then I'm saying that I'm taking the floor function, means I'm taking the maximum integer. So then I can set this is to be equal to 1 or this to be equal to 2 and this to be equal to 2. Then I have to add one more dummy digit here, right? So that dummy digit, okay, I can use some 0 for all the input of a length sequence. Okay, I can put that 0 to everything. Okay, I mean if I use that particular channel digit. Now, so now there are 2 to the power L possible inputs for the channel encoder. Guys, can you hear me?
Yes, sir.
Yes, sir.
Hello?
Yes, sir.
Yes, sir. Yes, sir. We can hear you.
Okay. So what I was saying, yeah. So there are 2 to the power L possible inputs for the channel encoder, because say this was my channel encoder. Okay, this is my channel encoder, and I'm sending L length, okay, binary digits, and then it will pass through the channel, let's say a sequence of n, okay, and this is channel digits. Okay, and so number of possible inputs here for the channel encoder is 2 to the power L. So for each such 2 to the power, each such sequence, each such L length sequence of 0, 1, I need to produce one sequence of channel digits of length n, right? So basically, so I can call this as code words, because I may use some other scheme instead of binary code. I may use ternary something else for my channel digits. So let me write this as some number to the power L, because every time if I write to the power L, so instead of that, suppose m is the number of elements here in the input, which is 2 to the power L, and for each such sequence of binary digits, I have to produce a sequence of channel digits of length n, capital N. So how many inputs are there? It is 1 to m. So for each m, okay, 1 less equal to this less equal to m. There are m such input, okay. We need to produce a code word of length n. So that means what I'm saying, let's say code words are, for example, or let's say, let me write it here, x bar m. Okay, then what is happening for what is my x1? X1 will be something like x11, x12, x1n. Okay, and then x2 I can also write something like x21, x22, okay, some x2n, and keep on doing that. and finally some x bar m capital M should be equal to x m1, x m2, and dot 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 x mn. Okay, so this is what I have to do. Okay, but I don't know what is n, but I'll come to that. I said n is equal to this. How do I decide the value of n? This is the recipe. This is how I can do that. Okay. Now let me give you an example. Okay. Now see here, there is a connection. Okay. What is the connection? If this is m to the power l, this corresponds to an integer. So this m is an integer. But if you take the binary representation of that integer, okay, then that will give you an element of this input. So if you take any integer from 1 to m, then you can take its binary representation and that will give you an ln sequence, okay, because 2 to the power l equal to m. It's just an observation. Now let me give you an example. Let us say this is an example. So let us say my TS, okay, this is 5 second, okay, 5 second. And let's say my TC, the channel time interval for one channel digit. Okay, TS is for the source time interval for one binary digit. So TC is 2 seconds. And let's say what I want to say input. Let's say my input is like this. L is equal to, let's say L is equal to 2. So that means I want 2 to the power 2, and 4 binary sequence I have. These are the inputs. 0, 1, 1, 0, and 1, 1. Okay, so these are the inputs, and then what is the value of m? Here it is 1, 2, 3, 4. Okay, these are the values. M equal to this. Okay, m equal to 4. I mean capital M equal to 4. So yeah, so this is the m equal to 1, 2, 3, 4. Yeah. Then what should be my code word? What should be the value of n? Can anybody tell me? What should be n? How do I decide the value of m?
LTS by TC.
So what is that?
5.
5. Okay. So this will be 5 by 2 times L, which is 5 by 2 times 2, which is equal to 5. Now let me denote this. Let's say my first, I want anything, right? So let me say this, I'm just giving an example. Let me say this is of length 5. Let me say, I can do it anything, but let me just give you an example like this. And let me say 2, 2, 1, 0, 1, 0, 2, 2, 2, 2. Let me say, I'm giving you an example that the channel digits need not be the binary digits. So I can now send this and see these are length 5, each of length 5, and there will be this channel will be completely synchronized. So there will be no delay. Okay. So once you give an input of length 5, length 2, then the channel will send a length channel digits here 0, 1, 2, okay, of length 5. Okay, so there will be no channel delay because for source it takes more time, and for channel it takes less time. So that's why I can increase my length, okay, for each of these inputs, okay, and then I can send it, and then this is how it works. Okay, now I'll define. So what is there any measure, okay, like which can tell me what is the how my communication system, let's say channel or whatever it is, how it is it working? Can I, guys, just I'm coming in 1 minute. Yeah, can you hear me?
Yes, sir.
Okay, actually, I had to take something out from a refrigerator because I have to cook in the evening. If I don't do right now, then I'll be in trouble. Okay, so yeah. Yeah, so yeah, I want some measure which can give me some idea about how my channel communication works, or I want to have a sense of, something which will guarantee to calculate the error probability. I'll define what is error probability. So
Sir,
if there is, yeah.
sir, it is necessary to take a length of exam equal to n, like 5 digit.
Yeah, so if you take that, then there will be time is synchronized. So here,
Sir,
yeah.
yes, sir, that I got. But sir, if you take less, then what will happen?
Then there will be a time gap. Your channel will be idle for some time.
Yes, sir.
So that is what is the thing. So it will not be synchronized. And if there is some kind of a delay, so you don't want that, because you want a continuous process, so that whenever it is giving an input, immediately you're producing the output. Otherwise, this will give you some input and you'll be waiting for some more input and so on. And then at a strength, you cannot send everything else. I mean, you cannot send at one go. So you have to wait for some time, and then this you means the channel encoder. It has to wait for some time, and then again next bunch comes together, okay, and then it has to send something else. So in order to minimize the time gap, so in order to make it synchronize the entire system, so you can have this this condition like n is equal to, what is that, ts by tc times l. So time is synchronized here. This is only the, so this is a technical thing, but this is theoretically how we can deal with it.
But sir, we have to send some extra bit.
Yeah, so if that is not like here, it is good to have an integer. If it is not, then suppose it is 5.1, then I'll take it that as a 6. Okay, so everywhere I'll put some 0. Okay, I'll put some 0, then I'll make that to be 6. And you will see later, this is very, very useful when you, because so this is one part of the game. So next part is you also have to decode, meaning whenever something is going like this kind of a thing reaches to the decoder, then it also has to produce this. So sometimes you can do this ad hoc things in such a way that even if there is a flip of some digits here, you can retrieve what is the original sequence is. Okay, so that will also be helpful, which I'll be discussing later on. So this is called something called error correcting. Okay, even if there is some error, I'll make n little large. So I'll send you some ad hoc. I'll send some ad hoc bits, let's say here, such that using those, I can see, okay, whether there is an error happened or not. Okay, and I can get back to my original. So from here to here, I can get back to the original using this ad hoc bits. You understand what I'm saying? So the thing is, I mean,
Yes,
the
sir.
matter, yeah, so matter does not end here. This is my point. Okay, we'll discuss about that. Okay, so the matter does not end here. So at that now, I'm just saying that it is time delay. I have to synchronize the time, so that's why I'm doing it. And then we'll see later. Okay, on top of that, what we can do in correcting the errors, if there is any error during I mean, when this sequence of binary channel digits is passing through the channel, okay, that may get corrupted, and then so then how to remove the error. Okay, we'll talk about that. So now what we'll define is, so we need something, okay, which will give you a measure how, let's say, to understand what is the property, or what is the characteristic of your channel or the channel code, okay, or the block code itself. Okay, so we define something called the rate. the rate, we denote it as R, okay, of, so here I'm coding in terms of block. You see here, this encoding scheme is different from the source encoding. Okay, this is completely different. Here I'm coding in terms of a block. You give me a sequence of L binary digits, then I'm creating a sequence of N channel digits. So it is encoded in terms of a block. Okay, this is not about individual source letter. Okay, it is given in terms of a block, complete block. So that's what it's called, a block encoding or block coding. So the rate of a block code, okay, is, this is how it is defined. So this is my definition. So is defined as this. This is called log of m. This m is 2 to the power L by n. Okay. So if you write this, this is log of 2 to the power L by n, which is L by n log 2. Okay, the base 2. This many bits. You can say this many bits. Okay. So if this guy is an integer, so this is how it is. N by L, this is TS by TC. If this is an integer, okay. So if L by N is an integer, okay, or instead of L by N, let me say like this. L times TS by TC. If this is an integer, then N is an integer, right? If this is an integer, then R is equal to what? TC by TS log of 2 is bits. So this is what is called the rate of the block code. So rate of the transmission, something like this. This is log of m divided by n. Okay. So what does it mean? Okay. So sometimes you will see this communication engineers. Okay. They will say, if you talk about a communication channel, then they will say like, what is the rate of your channel? Okay. They'll talk about what is the data rate. What is the data rate? They'll talk about that. Okay. So by data rate, what they actually mean that the number of binary. So let me write it. What is called. So this is a popular term for engineers. So they call it a data rate. Okay, data rate. So what they mean is that this is the number. This is the number of bits or binary digits. Okay, per second. Okay, that enters into okay, the transmitter, which will transmit. So here what we are defining this rate, and there is a little difference because we are also dividing it by n. Okay, we are also dividing with this n. Otherwise it is just L. You see, it is just L. But here we are dividing it by L because log 2 is actually 1. Okay, so yeah, so we are dividing by n. So it is so here it is normalized. That way you can say it is normalized. Okay, normalized means so how many you are sending and how I mean what is the input divided by how many digits you are giving output. So it is like a normalized thing. Okay. Okay. Yeah. So and sometimes okay you can also use okay there is yeah you can also use other basis like instead of bits you can also use a natural basis like you can take log e or log 10 whatever it is. Okay, some nats per digit also you can say, and then of course you can convert this into bits. Okay, yeah. Okay, so now we'll talk about little bit about decoding. In fact I think that we have to make a trade-off. Trade-off meaning what? If I want to prove the source coding theorem, it will take a long time first to develop develop the concept, meaning I need to prove 5-6 theorems, and then only I can talk about the proof of this source proof of this channel coding theorem. So, and if I do that, then the problem is I'll miss a lot of things about how this block coding is done. Okay, so there are different techniques to do this block coding, and then how to minimize error. So because minimizing error is a fundamental property of the channel, you may forget about channel capacity, this and that. I'll show you later maybe at why you are bothered about error, because even if you send decreasing, if your source entropy is less than the channel capacity, but if there is a lot of error, there is no meaning, right? So a lot of errors should be, the probability of error should be minimized. That's the prime focus, okay, for designing of a communication system or understanding a characteristic of a communication system. So I don't know whether so, and there are a lot of techniques, okay, for this block encoding, okay. And so like linear block encoding, where you will require linear algebra, and then there is something called convolution code, which is also very important, and Solomon code, and what is that? So Hamming code. So a lot of coding techniques are there, and how there's different kinds of coding techniques, block encoding techniques, okay, will help you to analyze the corresponding error. So that is also a prime prime concept of coding theory. So if I just prove this channel coding theorem, so then I'll lose this. So I'll miss this. So the thing is, I think so what do you want? So I can do whatever we want. Because if I skip, and I must tell you, this coding theory part will be comparatively easier than proving the channel coding theorem. So what do you want? So that, because the problem is I kept counted this thing. I think we have 10 lectures. Okay, I think there are 4. Yeah, I think approximately 5 weeks. Okay, before we have to end everything by L exams by 14th of April. Okay, I think we have 5 weeks, and there will be exams and there will be vivas. So you may forget about at least 4 classes. So that means we are left with at max 6 classes. Okay, but 6 classes is huge. That is not a problem, but we cannot do both. Okay, I think this is a 16th lecture. So already we are talking about, let's say, almost 30 hours. So, so what do you want? To focus on coding theory or the channel coding theorem? Hmm? Can you guys hear me?
Yes, sir.
So what do you want?
So related to whatever we have done past.
Okay, anything else? Anybody? Anyone wants to say anything? Okay. Nobody wants to say anything, or nobody is here except Gautam?
Sir, we are here, but we don't know. Means
Yeah, Risu, tell me. We don't know what. I mean, he can say whatever you think.
yes, sir, coding part is interesting currently, which is going on. But for further more topic, we don't know. We don't have any idea. So it's up to you.
Okay. Okay. Anybody else? Others? Vandana?
Yes, sir. I think maybe we should continue with the coding part that you're explaining right now.
Okay. So Yeah, and maybe if I get time, then probably I'll again get back to this channel coding theorem. Okay, I'm proving channel coding theorem, but I don't think we'll get time if we start talking about coding there. I mean, there are a lot of things. Okay, we'll see. Okay, we'll see. Maybe we'll focus on coding, but let us see. I mean, how far we can go. Okay, so yeah, so our definition of engineers will say half part second. Okay, so this is for the engineers, but for us, it is a little bit normalized. Okay, it is normalized. So there is an n here. Okay, which will divide by this. Now, okay, so suppose you send some x. Okay, let's say xm. Okay, bar. This is the input. Okay, so first you had this some, let's say u bar, let's say L. Okay, this is L length some binary digit. Now you send this, you convert it to some XM bar, which contains n number of channel digits, and then you transmit it. Okay, so this is transmission through the channel. Okay, and then what you get is something called, it's a Y bar, which is of length n. So which is, let's say, Y1, Y2, or you can write YM. So here you'll get some Y. Okay. So here I'll get something Y, let's say M1, YM2, Y, sorry, MN. So this is what you get. And then this will be converted. So there will be a channel decoder here, channel decoder. And here it will be some V, let's say, so some VL bar. Okay, so then it will give you the message. Okay, so this is the output, let's say, YM bar after it goes into the channel. Okay, so and this is the code word for that. Okay, this is the code word input. This is the code word for mth message. Mth message means this is a sequence of length L, which is a binary sequence. So which is a string of L binary digits. Okay, this is the code word for that. Okay, and then you will receive this. Okay, and this is happening for all possible sequence of capital L, length capital L. Okay, sequence of binary digits of capital L. Now, when do we say there is an error? Okay, in fact, we'll say there is a block error. Okay, block decoding error. So we say, or we define, or we say, let's say, okay, that a block decoding error has happened. Okay, if the code word obtained by the decoder okay is different from the input of the encoder. Like here, now if you just see here, let's say x, and so you can say this to be equal to some x m1, okay, x m1, x m2, x some m n. Okay. Now see, what can happen is at one particular place, okay, the error can happen, or Okay, error can happen at multiple places. In fact, when we say this block decoding error, we can generalize this thing and we can say this is between UL bar and VL bar. So when you send something here and after decoding you receive something here, then there is an error. So there was a sequence H1 or let's say L1, UL1, UL2, ULL, okay, and then you produce something VL11, VL, VL2, VLL, and then at one particular place there could be error, or at multiple places there could be error. In fact, if your channel is memoryless, then the error depends only on the corresponding position. Okay. Now, what we are interested here is in the fact that how we can minimize this kind of an error. Even if there is some error, then how to minimize this kind of an error. So there are two things. One is this could be a chance of error, or you can say, of course, that if you have some XM bar and there is an error, okay, the channel corrupts this, and this is some YM bar. Okay, this is some error occurred. So here is what is happening. The message. This is what I'm calling is M stands for the message. So when this is transmitted through the channel and this you receive the received message, then this message corresponding to an integer, let's say M. See, as I said, this mth input is corresponding to an integer between 1 to capital M. Okay, so this is M, and this is something called, let's say, some integer, which is M dashed. Because 2 to the power L is equal to M, capital M. And so this is the set of all sequences of length L. So if you take any integer from 1 to M, so there is a corresponding sequence of 0, 1. Okay. So we can say that this M is an integer and you get an integer M dashed. So if M is not equal to M dashed, then there is an error. Okay. Okay. Now we have to analyze how do I define this error. And there are many more things, but okay. So I think let me go directly to this error business. Okay. So now we have to define some notations. Okay. Now I'm thinking whether should we do it or maybe I'll leave it for the next week. Start doing it. Yeah, I think we'll leave it here, and I would continue this next day, or the error probability and different mechanisms of block encoding. So the books which I asked you to follow as references, okay, those books do not contain this block encoding part in great details, okay. So you need to read another book, which is by Richard Hamming. So there is a code called Hamming code, and that book is written by him. So I'll mention this book. I mean, the title of the book is something called The Algebraic Coding Theory or something like that. Okay. So I'll update my web page of this course, and there I'll mention what is the title of this book. And then you can follow that book for whatever I'll be discussing next, okay, on block encoding. Okay, guys, you have any question?